Welcome to this problem-solving session. In this video, we'll tackle LeetCode problem number 1250, check if it is a good array. This problem introduces a fascinating twist on arrays and the concept of the greatest common divisor, GCD. Let's dive in and explore the challenge together. In this problem, we are tasked with determining whether a given integer array, called nums, is a good array. An array is defined as a good array if the greatest common divisor, or GCD, of all its elements is equal to 1. To solve this, we need to return true if the array is good, and false otherwise. The input is an integer array, nums, where its size can range from 1 to 10,000. Each element in the array can be as large as 1 billion. Our output is a single Boolean value indicating whether the array meets the conditions of a good array. Let's look at some examples to clarify the concept further. First, consider the input array nums equals 12, 5, 7, 23. The output for this example is true because the GCD of all the elements in this array is 1, which satisfies the condition for a good array. Here's how the GCD is calculated step by step. First, we compute the GCD of 12 and 5, which is 1 using the Euclidean algorithm. Since the GCD is already 1, we can stop further calculations, as the GCD of any number with 1 will always remain 1. Therefore, this array is classified as a good array. Another example is nums equals 29, 6, 10. Here too, the output is true because the GCD of all the elements is 1. Step by step, we compute the GCD of 29 and 6, which is 1. And since the GCD is 1 at this stage, the array is a good array. Now, let's analyze a different case with the input array nums equals 3, 6, 9. The output here is false because the GCD of all the elements in the array is 3, which does not meet the condition of being equal to 1. Here's how the calculation works. First, we compute the GCD of 3 and 6, which is 3. Then, we calculate the GCD of 3 and 9, which is also 3. Since the final GCD is 3 and not 1, this array is not a good array. From these examples, we can conclude that a good array must have all elements combined in such a way that their greatest common divisor is exactly 1. Looking at the constraints, we see that the length of the array can be as large as 10,000, and the values can go up to 1 billion. This means we need an efficient method to compute the GCD, such as the Euclidean algorithm, to handle these large numbers. An important edge case to consider is when the array contains a single element. In that case, the array is a good array only if the single element is 1, as the GCD of a single number is the number itself. Additionally, arrays involving prime numbers may often result in a GCD of 1, making them good arrays, but this depends on the specific combination of numbers in the array. To determine if an array is a good array, we focus on the greatest common divisor, or GCD, of all elements in the array. A good array is one where the GCD of all its elements equals 1. One approach to solving this problem is the brute force method, which involves calculating the GCD of all possible pairs of elements in the array iteratively. The idea is to start with the first element as the initial GCD and then compute the GCD with every other element in the array. If at any point the GCD becomes 1, we can stop immediately and return true, because once the GCD is 1, it cannot get smaller. On the other hand, if the loop completes without the GCD ever reaching 1, we return false. However, while this method is simple to understand, it is computationally expensive. Repeatedly calculating the GCD for all pairs of elements leads to a time complexity of n squared, which becomes impractical for larger arrays. The space complexity is efficient at 1, but the high time cost makes this approach inefficient overall for large datasets. A more efficient solution is the cumulative GCD approach. This method eliminates the need to compute the GCD for all pairs of elements by leveraging the mathematical property that the GCD of the entire array equals 1 if and only if the array is a good array. The steps are straightforward: initialize the GCD with the first element of the array, then iterate through the rest of the elements, updating the cumulative GCD with each new element. If the GCD becomes 1 at any point, we can immediately return true, as this guarantees the array is a good array. If the loop completes and the GCD has not reached 1, we return false. Key mathematical principles support this approach, including the idea that if two numbers have a GCD of 1, they can generate any integer through linear combinations, as described by Bazat's identity. This insight allows us to bypass exhaustive pairwise checks and focus solely on the cumulative GCD. The time complexity of this method is significantly improved to O and asterisk log max nums, where log max nums accounts for the efficiency of each GCD computation. The cumulative GCD approach also boasts an excellent space complexity of O(1), as it does not require any additional data structures or memory beyond the variables used for computation. What makes this approach particularly efficient is its ability to avoid redundant calculations by leveraging the mathematical properties of the GCD. This allows us to scale linearly with the number of elements in the array. After analyzing both methods, the cumulative GCD approach emerged as the chosen strategy because it is both mathematically sound and computationally efficient. The key realization was that the entire problem hinges on the cumulative GCD of the array. Once we understood that the GCD becoming 1 guarantees the array is a good array, we could eliminate the need for pairwise comparisons entirely. This aha moment significantly simplified the solution while ensuring its accuracy and efficiency. When comparing the two approaches, the brute force method stands out for its simplicity but is ultimately impractical for larger arrays due to its high computational cost. Redundant calculations make it inefficient, especially as the input size grows. In contrast, the cumulative GCD approach is far more efficient, directly leveraging the properties of the GCD to minimize unnecessary computations. It also allows for early termination, which further enhances its performance. For these reasons, the cumulative GCD method is the recommended solution. It is optimal in terms of both time and space complexity, making it scalable, fast, and perfectly aligned with the problem's requirements. By avoiding redundant work and focusing solely on the core mathematical insight, this approach delivers the best balance of simplicity and efficiency. The problem we're tackling is to determine whether a given array qualifies as a good array. An array is considered good if the greatest common divisor, or GCD, of all its elements equals 1. To solve this, we need to leverage a key mathematical insight about the GCD. Specifically, the GCD operation is associative, which means the GCD of three numbers, A, B, and C, can be computed as GCD, A, B, C. This property allows us to simplify the problem by iteratively reducing the array to a single GCD value. To start, we'll initialize a variable, which we'll call current_GCD, with the first element of the array. This variable will hold the ongoing GCD as we process the rest of the elements in the array. The next step is to iterate through the array. For each element, we compute the GCD of the current value of current_GCD and the array element, then update current_GCD with the result. To perform this calculation efficiently, we use the Euclidean algorithm, which is well known for its logarithmic time complexity. One important optimization here is early termination. If at any point current_GCD becomes 1, we can stop iterating immediately. This is because the GCD of any number with 1 is always 1, so further calculations become unnecessary. After completing the iteration, we simply check the final value of current_GCD. If it equals 1, we return true, indicating that the array is good. Otherwise, we return false. The efficiency of this approach lies in the Euclidean algorithm, which operates in O, log, min, A, B, time for two numbers. For the entire array, the time complexity is O, n asterisk log, max_element, where n is the array size, and the space complexity remains constant at O, 1. Early termination can further reduce the runtime, especially for large arrays where the GCD quickly reduces to 1. To implement this algorithm, we rely on two simple data structures. First, the input array itself, which we process linearly. Second, a single integer variable, current_GCD, which stores the running GCD during the iteration. Now, let's consider some edge cases. If the array contains only one element, it is good if and only if that element is 1. For arrays where all elements are identical, the GCD is simply the value of those elements. In this case, the array is good only if that value equals 1. Lastly, consider arrays that include zeros. Since the GCD of 0 and any non-zero number is the non-zero number itself, zeros in the array do not affect the result, provided there's at least one non-zero element to work with. Let's walk through an example with the input array 8, 12, 15. First, we initialize current_GCD to the first element, which is 8. In the first iteration, we compute the GCD of 8 and 12, which is 4, and update current_GCD to 4. In the second iteration, we compute the GCD of 4 and 15, which is 1, and update current_GCD to 1. Since current_GCD is now 1, we terminate the loop early, as further calculations are unnecessary. Finally, we return true because the array qualifies as a good array. Analyzing the complexity, the time required for this example is proportional to n*log max_element, where n is the array size and max_element is the largest value. The space complexity remains 1, as we only use a single integer variable for calculations. This implementation solves the problem of checking if an array is a good array. The key insight is that an array is considered good if the greatest common divisor, GCD, of all its elements equals 1. If the GCD is 1, it means the numbers can form a linear combination that equals 1. The solution uses the math.gcd function, which efficiently computes the GCD of two numbers. The algorithm starts by initializing the GCD with the first element of the array. Then, it iterates through the rest of the elements, updating the GCD with each new element. If at any point the GCD becomes 1, we can immediately return true, as further computations are unnecessary. This optimization ensures the solution is efficient. If the loop completes without finding a GCD of 1, the function returns false, indicating the array is not good. This approach is efficient, with a time complexity proportional to the number of elements in the array and the cost of computing the GCD, which is logarithmic in the magnitude of the numbers. The implementation is concise and handles all edge cases, including arrays of size 1 and arrays with large numbers, by leveraging the properties of the GCD operation. Here, we start by importing the necessary utilities and defining our solution class. The method isGoodArray takes an integer array nums as input. The goal is to determine if the array is a good array, which means the greatest common divisor, or GCD, of all its elements must be 1. To achieve this, we initialize a variable current_GCD with the first element of the array. This will serve as our starting point for calculating the GCD of all elements in the array. Next, we use a for-each loop to iterate through each number in the array. Inside the loop, we update current_GCD by calling our helper method GCD on the current value of current_GCD and the current number in the iteration. If at any point the GCD becomes 1, we know the array is good, so we return true immediately to save computation. Otherwise, if the loop completes and the GCD never reaches 1, we return false, indicating the array is not good. The helper method GCD is implemented here using Euclid's algorithm, which is an efficient way to compute the greatest common divisor of two integers. The algorithm works by repeatedly replacing the larger number with its remainder when divided by the smaller number, until the remainder becomes 0. When that happens, the smaller number is the GCD. In the code, we use a while loop to continue this process as long as b is not 0. Inside the loop, we store the value of b temporarily, update b to be the remainder of a divided by b, and then set a to the temporary value. Once the loop ends, the variable a will hold the GCD, which is then returned. This helper method is crucial for the main logic as it ensures we can efficiently compute the GCD of any two numbers in the array. To solve this problem, we start by examining the input array nums equals 12, 15, 35. The goal is to check if the greatest common divisor, or GCD, of all the numbers in the array equals 1 at any point during the computation. First, we initialize current_GCD to the first element of the array, which is 12. Now, we begin iterating through the numbers. In the first iteration, the current number is 12. Calculating the GCD of 12 and 12 results in a current_GCD of 12, so there's no change. Because the GCD is not 1, we move to the next number. In the second iteration, the current number is 15. Now, we calculate the GCD of 12 and 15, which gives us 3. Since the GCD is still not 1, the process continues. Finally, in the third iteration, the current number is 35. Calculating the GCD of 3 and 35 results in a current_GCD of 1. At this point, the condition is satisfied, and the function immediately returns true. Here, the output for the first example is true because the GCD became 1 during the iterations. Moving to the next example, the input array is nums equals 4, 8, 16. Again, we initialize current_GCD to the first element, which is 4. In the first iteration, the current number is 4. Calculating the GCD of 4 and 4 gives us 4, so current_GCD remains unchanged. Since it's not 1, we proceed. In the second iteration, the current number is 8. This time, the GCD of 4 and 8 is also 4, so the value of current_GCD again remains the same. As the GCD has not yet reached 1, we continue with the process. In the third and final iteration for this example, the current number is 16. Calculating the GCD of 4 and 16 results in a current_GCD of 4, which again remains unchanged. At this point, the loop ends, and since the GCD never reached 1, the function returns false. For the third example, the input array is nums equals 7, 21, 28, 35. We initialize current_GCD to the first element, which is 7. In the first iteration, the current number is 7. Calculating the GCD of 7 and 7 gives us a current_GCD of 7, so there's no change. Since the GCD is not 1, we proceed to the next number. In the second iteration, the current number is 21. Calculating the GCD of 7 and 21 gives a current_GCD of 7, so the value remains the same. Since it's still not 1, the next iteration begins. In the third iteration, the current number is 28. The GCD of 7 and 28 is again 7, so there's no change to current_GCD. Finally, in the fourth iteration, the current number is 35. Calculating the GCD of 7 and 35 results in a current_GCD of 7 once more. The loop ends, and since the GCD never became 1, the function returns false for this example. The time complexity of this solution is determined by analyzing the two main components of the algorithm. First, we have a single loop that iterates through all the elements in the input array nums, which contributes an O(n) factor to the complexity, where n is the number of elements in the array. Second, within this loop, the GCD function is called to compute the greatest common divisor of two integers. The time complexity of the GCD function, based on the Euclidean algorithm, is O log min a b, where a and b are the integers being compared. In this case, the maximum possible value of any element in the array is max a_i, so the GCD computation can take at most O log max a_i. When we combine these two parts, the total time complexity becomes O(n) log max a_i***. Now, it's worth noting that in the best case, the GCD becomes 1 early in the loop, allowing the algorithm to terminate after just a few iterations. In such cases, the time complexity is closer to O(k** log max a_i***, where k is the number of iterations before termination, making the algorithm even more efficient under certain conditions. In the worst-case scenario, the algorithm must process all elements in the array, performing the GCD operation for each pair. This means the algorithm cannot terminate early and must iterate through the entire array, resulting in a time complexity of O(n** log max a_i***. Now, turning our attention to space complexity, the solution is highly efficient in this regard. The space complexity is O(1), because the algorithm only uses a constant amount of extra memory. Specifically, the current_GCD variable, which stores the running GCD of the array elements, is updated in place during the loop. Additionally, the GCD function itself operates iteratively using the Euclidean algorithm, which does not require any extra memory. Furthermore, the solution does not create any additional data structures, and the input array nums remains unchanged throughout the computation. These factors ensure that the overall space complexity remains constant, making this approach not only time efficient but also memory efficient. To appreciate the efficiency of the current solution, let's compare it to a naive or brute force approach. A brute force method would involve checking all possible linear combinations of the array elements to see if any combination sums to 1. This would require generating all possible subsets of the array and computing their sums, leading to an exponential time complexity of O2 to the power of n, due to the subset generation and some checks. In contrast, the optimized solution leverages a key mathematical property: an array is good if and only if the greatest common divisor of all its elements is 1. This eliminates the need to compute all combinations, reducing the time complexity to O n asterisk log max a underscore I asterisk asterisk. The mathematical proof of this complexity stems from the fact that the GCD operation for two integers has a complexity of O log min a b using the Euclidean algorithm. Since the algorithm processes all n elements in the array, and the maximum possible value of any element is max a underscore I, the total complexity for all GCD computations is O n asterisk log max a underscore I asterisk asterisk. This approach is significantly more efficient than brute force methods, making it an optimal solution for this problem. When tackling this problem, there are some common mistakes to be aware of. First, assuming that the GCD of all elements is the same as the GCD of adjacent pairs is a major pitfall. This is because the GCD of subsets of elements doesn't necessarily determine the GCD of the entire array. For instance, while the GCD of 3 and 6 is 3, introducing another number, like 10, changes the GCD of the entire array to 1. It's essential to compute the GCD cumulatively across the entire array. Another common mistake is not handling edge cases properly, such as arrays with a single element. A single element array like 1 should return true because the GCD of 1 is 1, but improper handling could lead to false negatives. Additionally, using a brute force approach to calculate the GCD for all pairs in large arrays is inefficient. This method has a time complexity of O n squared, which becomes impractical for larger inputs. Instead, a cumulative GCD approach with linear complexity is much more efficient. Lastly, misunderstanding the problem is another frequent error. Remember, it's not about finding subsets with a GCD of 1, but about ensuring the GCD of the entire array equals 1. Now, let's address potential variations and insights that can help in an interview setting. One potential issue involves overflow when dealing with large integers during GCD calculations. Certain programming languages may encounter this issue, so it's advisable to use modular arithmetic or built-in GCD functions to mitigate overflow risks. The key pattern to recognize here is that the GCD of multiple numbers can be computed iteratively, using the property that GCD A, B, C is equivalent to GCD A, B, C. This iterative approach is efficient and forms the basis of the optimal solution. By leveraging the Euclidean algorithm, you can compute the GCD of the array in O n asterisk log max a underscore I time, which is both efficient and suitable for interviews. Pay special attention to edge cases, such as very small arrays like 1 or 2, arrays with repeated elements like 3, 3, 3, and arrays with coprime numbers like 6, 10, 15. Additionally, be prepared for follow-up questions, such as modifying the approach to find subsets with a GCD of 1, handling dynamic input where the array elements change over time, or optimizing the solution for scenarios like real-time streams of data. There are several related problems and alternative approaches worth exploring. For instance, LeetCode 1250 is the direct match for this problem, while LeetCode 1979 is a simpler version focused solely on finding the GCD of an array. Problems like LeetCode 1447, which deals with simplified fractions, and LeetCode 914, which uses GCD to check divisibility, are also relevant due to their reliance on GCD calculations. As for alternative approaches, one option is the iterative pairwise GCD method. While easier to implement, it's slower with a time complexity of O n squared, making it suitable only for small inputs or as a brute force baseline. Another alternative is the cumulative GCD approach with early termination. This strategy allows you to stop as soon as the GCD reaches 1, which can be highly efficient in the best case, reducing the complexity to OK. However, in the worst case, it still aligns with the optimal O n asterisk log max a underscore I. This technique is particularly useful for competitive programming where saving time is critical. Another alternative approach to consider is using prime factorization. While this method is conceptually interesting, it comes with significant computational overhead. The time complexity is approximately O n asterisk sqrt max a underscore I, which makes it impractical for handling large numbers or arrays with many elements. As a result, prime factorization is rarely used in practice for this type of problem. However, understanding it can be valuable for theoretical purposes or for problems that specifically require factorization. In general, it's better to rely on more efficient methods like the iterative Euclidean algorithm or cumulative GCD with early termination for practical applications. Great job! In summary, we explored how to check if an array is good using the GCD concept. We discussed the algorithm, its time complexity, and key takeaways. Thanks for watching. Don't forget to like and subscribe for more coding tips and tutorials. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!